Can you see my screen?
Yes, I can see your screen. Yep. Okay. So, yeah, I can see your
Th-
screen. So, not a problem. Yeah.
Thank you.
Okay. Thank you, Aliska. So I think it's time to start. So, a very good day to everybody joining right from different parts of the world. Good morning, good evening. I guess no one in is good afternoon, but good day to everyone. So, this is Reliability and Safety 5 session, and we have a very exciting presentation coming up. So, it will be a four presentations to be given by first by Cha Yang and then by Hao Sun, followed by Aliska, and the final presentation will be given by Caroline. So each presentation is around 5 minutes, and after the presentation, we're gonna have like an open discussion session. So anytime you have a question up to the presenter, please write the question on the chat, and after all the presenters have made their presentation, we can then discuss the questions one at a time. Okay, so let's first invite our first speaker, which is Chia Yang. And Chia Yang will present his work titled When Cyber Physical System Meet AI, a Benchmark, an Evaluation, and a Way Forward. So Chia Yang, please.
Yeah, thank you, David. Hi everyone. I'm Jia Yang a first-year PhD student at University of Alberta. So today I'm going to briefly go through our work for this XC conference, One Cyber-Physical System Meets AI, a benchmark and evaluation and the way forward. So basically our work is to establish the first benchmark to review the characteristics of AI-enabled cyber-physical systems. Since like nowadays, CPS is a core concept to implement the fourth industrial revolution. And more CPS applications are adapting the AI components inside the control or prediction, even optimization process. But people are lacking on some, I would say, deep understandings about the capability and characteristics of the AI components. Specifically here, we are going through the control loops for the AI controllers, mainly the deep reinforcement learning used in control loops. Things like the reinforcement learning is the really sought out technologies to implementing the control systems nowadays. And so our motivation is to just give the community, both the traditional software engineering and the AI communities, a platform to let them go through their developing the algorithms or testing their methodologies. So this is the research workflow of our work. For first, like we need to collect the benchmarks from the diverse source, but many of them are focusing on the MATLAB Simulink platform. Things like most of the CPS are really complicated systems. The dynamics hiding behind the entire platform is complicated and it's hard to be handled by some like script-based programming language like Python. But Simulink is the really advanced and solid platform used by both the academia and the industrial to implement these CPS models. So as we collect several CPS systems like the adaptive cruising control system, land keeping system, powertrain, and wind turbines, we have trained multiple deep reinforcement learning based AI controllers with like different algorithms, configurations, and twisted reward functions to explore the capabilities, the boundaries of the AI controllers. Then we evaluate both AI and traditional controllers from multiple metrics to compare their performance. Then we also like to use the traditional testing techniques. I mean the falsification. Falsification is a really commonly used traditional testing tools to evaluate the performance for defect detection of traditional softwares. So we want to explore whether this traditional technology is still effective is still effective in the when the CPS embedded with AI components. So the third one as I said, we have AI controllers on our hands with like the traditional controllers like MPC or PID. Can we combine them, make a hybrid one to make this hybrid control system outperform any of the single ones? So just let me quick go through the result part. Mhm. So for the first one, like we compare the performance between the AI ones and the traditional ones, and they find like um, in most of the benchmarks we collected, the AI ones have equally good or even beyond the performance. But when a complicated system have like multiple operation requirements, like they need to satisfy different requirements on like maybe velocity, distance, stability, or like resilience, the AI controllers may have troubles on that since you need to define reward functions to guide the training process. But there is this reward function, if it is composed many requirements, one requirement may overshadow another. So the AI controllers may have shortages on this part to dealing with multiple operation requirements. And for the result of the falsification, we found like the falsification algorithm, the hill climbing algorithm we here cannot effectively defect the defections on AI components. We have plotted the hyperplan of the control behaviors, and we find that that hyperplan has filled with a bunch of local minimas, and the hill climbing algorithm can easily fall into maybe one of them, the local minima, and cannot get the global one. So the falsification cannot effectively falsify the AI embedded CPS systems. And move to the controller hybridization, the last one. We use like different hybridization methods, like randomly select the control signals or using the averaged ones, or set some scenarios to dynamically switch between different controllers. And we surprisingly, like we find these hybrid ones definitely or significantly can outperform the others because they can take the advantages from different subcontrollers to make a more advanced and beyond or polished one. So some conclusions like first, as I said, reinforcement learning or AI-based controllers may have shortages to balance different control requirements, and the existing falsification algorithm need to get some informations inside the AI components to better falsify or evaluate the AI embedded CPS. And the third one, the combination of hybrid controllers can offer a new direction to improve the safety and reliability of AI CPS. Yeah, that's basically the same thing as I said. So yeah, that's a brief go through of my work. If you have any questions, just let me know. I'm happy to answer.
Yes, thank you very much, Xiaoyang, for a nice presentation. So if anyone has a question for Xiaoyang, please feel free to just write them on the chat. And then at the end of all the presentation, then we're going to discuss the question with Xiaoyang and all the speakers and everybody. Right, so thank you, Xiaoyang. So now we're going to invite the second presenter will be Hao Chen. So Haochen will be presenting his work on multi-intention aware configuration selection for performance tuning. So Haochen, please.
Okay, thanks for the introduction. I'm Hao Chen. I'm very glad to share our work with you. This work is toward to a limitation of current performance tuning tools, that they usually only focus on performance but not aware of other important user intentions. In production, users usually use configurations to satisfy their intentions. Common intentions are like increasing performance, keeping reliability, or enhancing security. As the scale of software system becomes larger, the number of configuration parameters increase rapidly, and the number even goes beyond 1,000 in some software. It is obviously impossible for users themselves to choose from hundreds to thousands of parameters to fulfill their intentions. So many works have been proposed to alleviate this problem. They build performance models or train auto-tuners to help user improve performance. But the efficiency of these tuners is extremely limited by the combinatorial explosion problems of configuration parameters. So some works pre-select some performance-related parameters to reduce the search space via performance testing and machine learning techniques. However, both these pre-selection methods and the auto-tuning methods only consider performance while ignoring other user intentions. In fact, many parameters have more than one side of impact on their user intentions, on other user intentions. For the example in MyCircle, the parameter InnoDB flush log at transaction commit controls the trade-off between ACID compliance and performance. That is to say, these methods may possibly put users at the risk of bad issues like data loss. This is the main problems that we are going to targeting on in this paper. And from the efficiency perspective, these methods relies on performance testing, which is very heavy that limit their usefulness. In conclusion, a method that takes multi-intentions into consideration and selecting configuration parameters in a lightweight method is needed. So we propose SafeTune, an approach that's pre-selecting performance-related parameters with aware of other user intentions like keeping reliability. The usage of SafeTune is to help performance tuners improve efficiency as well as warn potential violations on other user intentions. Configuration documents are official description configuration parameters. Most mature software are equipped with these documents. And the insight is that the configuration document usually contains useful information that generally explain the affected user intentions. For these parameters, as marked in these slides, it is documented to have an impact on both performance and reliability. Another advantage of document is that it's more lightweight, that does not need heavy performance testing. So the main idea of SafeTune is mind the relationship between performance and other user intentions from configuration documents. Therefore, we made an empirical study on more than 7,000 configuration parameters and find out that majority performance-related parameters indeed affect other user intentions. And there are 6 types of intentions that may get affected. So based on the finding, we built a model to infer the side effects on user intentions given the configuration documents. The model applies a semi-supervised method to reduce the labeling effort and use a simple machine learning method to understand the semantics in the documents. Though simple, it can still achieve a good result. The comparison with the state-of-art method in hot storage 20 shows that the SafeTune can not only cover most parameters found by them, but also find 20 more parameters that have significant impact missed by them. We also evaluate SafeTune on effectiveness on helping popular auto-tuning tools. The result shows that with SafeTune, 12 severe side effects like potential data corruption in case A can be prevented. In this paper, we argue that the future tools should pay more attention on tuning with other target intentions like reliability and resource usage. Okay, thanks for listening.
So thank you very much, Hao-Chen, for a very nice presentation. So again, if you have questions for Hao-Chen, please feel free to write the questions in the chat, and then we're going to discuss that at the end of the presentations. So now we're going to go to the third speaker. So the third speaker will be Eliska, and Eliska will be presenting her work on deep stability, a study of unstable numerical methods and their solutions in deep learning. So Eliska, please.
Thank you, David. So my name is Ellie Cloverdance, and I'd like to present deep stability. Deep stability is a study of numerically unstable methods and their solutions in deep learning. And first, I would like to define what is numerical stability and its relevance to deep learning. Numerical stability is a property of an algorithm, and it comes from the fact that mathematically equivalent algorithms can have very different numerical properties. There are two primary types of numerical errors: round-off errors and truncation errors. The round-off errors arise from representing real values in finite precision, only with a finite number of bits. And the truncation errors arise from performing only a finite number of iterations for an iterative algorithm. The derivative calculation is a great example of that. And numerical stability governs how sensitive an algorithm is to these numerical errors. If an algorithm is numerically unstable, the result of that is that the outputs of it can be inaccurate or incorrect. And the relevance of deep learning of numerical stability is that in deep learning, we perform a lot of numerical computations in finite precision and often iteratively. The challenge of analyzing numerical stability in deep learning is that it requires interdisciplinary knowledge, including but not limited to numerical analysis, deep learning, and software engineering. And detecting and diagnosing numerical stability issues is difficult because those issues are often triggered only by a narrow range of inputs, and the errors can often occur silently and propagate through the network far from the origin of the problem. And finally, oftentimes the solutions to numerical instability can be very algorithm specific and therefore require algorithm specific knowledge. I'd like to give a motivating example of softmax, which is a commonly used function in deep learning. And the definition of softmax is shown in the formula on the left. However, if we implement softmax exactly as per this definition, it is actually numerically unstable. And to show that, we perform some experiments with this numerically unstable implementation, and we show that it outputs unreliable results. We can see that if we pass in the number 100 into softmax along with other numbers, it actually outputs nan, not a number. So that is not a very useful result at all. And the solution to this is to rewrite the softmax formula to make it more numerically stable. And we can do that by normalizing each input xi by subtracting the maximum of the entire vector x. And the results of this implementation that is numerically stable are correct. And also in our paper, we show a proof that these two formulas are mathematically equivalent. And this is a great example that demonstrates that mathematically equivalent formulas used in deep learning can have very different numerical properties and very different impact on the reliability of the results that they output. So we ask 3 primary research questions, and we leverage the commits in PyTorch and TensorFlow repositories to answer them. The first question asks, which deep learning algorithms are susceptible to numerical instability? And we find that it is operations within tensor math, such as exponential, logarithm, remainder, variance, standard deviation, etc., that are the most common ones that are susceptible to numerical instability, as well as operations in statistical distributions, data processing, and neural network quantization. The second question investigates what is the cause and impact of numerical instability in deep learning. And we find that the most common errors caused by numerical instability are overflow, loss of precision, and underflow, which in turn impact the quality of deep learning software by producing incorrect or inaccurate results and learning. The third question asks, what are the solutions for handling this numerical instability in deep learning? And we find that there are 4 most common solution patterns. The first one is rewriting the math formula by using different operations, reordering them, or adding a small epsilon, for instance, to logarithm. The second solution pattern is increasing the precision or changing the variable type. The third is using a different algorithm altogether. And the fourth is adding bounds check on the input range and limiting the input range to prevent numerical instability symptoms. In addition to answering those research questions, we have also made some discoveries. These 4 algorithms that are used in deep learning, we have discovered them to be numerically unstable, and this has not been discussed in prior papers. So we explain why they are numerically unstable and also provide a solution to make them more stable. In conclusion, we make 5 primary contributions. First, we identify which deep learning algorithms are numerically unstable and explain why. We perform an in-depth analysis of the root cause and impact of numerical instability in deep learning, and we provide both mathematical and code-level solutions to that. We also make some discoveries regarding some methods used in deep learning and identify them as numerically unstable, which has not been discussed in prior literature. And we compile all of our findings into a database that we call Deep Stability, which is the first database of numerical stability issues and their solutions. And it is publicly available, and the goal of it is to help deep learning developers and machine learning engineers to diagnose issues pertaining to numerical stability and fix them. And actually, we ourselves have leveraged this database we created and identified a numerical instability vulnerability in TensorFlow and submitted a fix that has been merged in and referenced our deep stability database along with the vulnerability and the fix, which is exactly what we envision for future developers to do.
So thank you very much, Eliska, for a very nice presentation. So again, if you have a question for Eliska, please feel free to write them on the chat, and we're going to discuss them very soon. So for our final presenter for this session will be Caroline, and Caroline will be presenting her work on If a Human Can See It, So Should Your System, Reliability Requirements for Machine Vision Components. So Caroline, please. Sorry, Caroline, you are muted.
Sorry about that. Okay, hello everyone. My name is Caroline. I am from the University of Toronto in Canada. Today I'm presenting our work in collaboration with University of Waterloo titled If a Human Can See It, So Should Your System, Reliability Requirements for Machine Vision Components. Machine vision components, MVCs, are currently deployed in safety critical systems, such as autonomous driving cars and medical imaging devices, where undesired behaviors can lead to fatal accidents. For example, the MEC in the Uber case failed to recognize a pedestrian and led to a crash. Such vision tasks are hard to specify. They are normally performed using ML. However, it is in order to check the correctness prior to deployment, one still needs to define what it means for an ML to be correct. In this work, we focus on one specifiable safety property, reliability against environment changes, such as the dark light in the Uber accident. This is commonly known as ML robustness. However, dark is not an invalid input or stressful condition studied by robustness, but a necessary normal deployment scenario. Therefore, in this paper, we refer to this property as reliability. In software engineering, reliability is the ability of a system or component to perform its required function in a specified environment in a specified period of time. We consider reliability of MVC as whether the performance of an MVC remains reliably unaffected by image transformations that commonly occur in real-world scenarios. Oops. Sorry. Lack of detailed and machine verifiable reliability requirements limit the ability to assess MVC reliability. Since MVCs are developed to automate human vision, we use human performance as a baseline to define reliability of MVCs against realistic changes in the real-world deployment environment. More specifically, if the changes do not affect humans, they should not affect MVC either. To this end, we specify 2 reliability requirement classes for MVCs with parameters representing human performance, correctness preservation, and prediction preservation. Also a method to instantiate them into machine verifiable requirements. Why does this keep changing? Requirements, and a method to check MVC satisfaction. As an example, consider the reliability of image classification MVCs against the transformation artificial frost addition, which is shown in the image on this slide. The instantiated correctness preservation requirement states the recognition accuracy of an MVC should not decrease if the visual change in the image is within the range delta V less than or equal to 0.84. And the instantiated prediction preservation states the percentage of labels an MVC can preserve after adding frost should not decrease if the visual change in the image is within the range delta V less than or equal to 0.91. In both requirements, delta V is our defined metric for measuring visual change in images, and the number 0.84 and 0.91 are estimated using human performance data. They represent the range of how much visual change does not affect human performance, which is the human tolerated range. Intuitively, in the 4 images shown here, the car is clearly visible for humans in the first 3 images. They are within the range we consider. And the last one, the car is no longer visible, and this one is outside of the range. Neither of our requirements substitute the other. Correctness preservation checks for the correctness of decisions, and the prediction preservation checks for the prediction of decisions. Correctness preservation requires prompt truth, whereas prediction preservation can be checked on unlabeled images. If an MVC satisfies only correctness preservation, it may correctly recognize different objects before and after transformation. And if only prediction preservation is satisfied, the MVC might preserve incorrect decisions and change correct ones. If both are satisfied, then the MVC is both correctness and prediction preserving, which is ideal. If neither is satisfied, then the MVC is neither correct nor prediction preserving, which is undesirable. As evaluation, we evaluated our range considered in the requirements by answering how well do the existing reliability evaluation methods cover the human tolerated range of changes. We showed that the state-of-the-art benchmark datasets for checking MVC reliability do not address the human tolerated range. We then are interested in how effective is our requirement checking method in identifying reliability gaps compared to existing approaches, and we discovered that by checking the satisfaction of our requirement, we can detect reliability gaps missed by state-of-the-art benchmark datasets. Therefore, we conclude that it is useful to use MVC reliability to check MVC reliability against our requirements. All right, thank you very much.
Thank you very much, Caroline. Very nice presentation. So, okay, so if you have questions for Caroline or any other speaker, please post them on the chat, right? And then we have still like half an hour for a very nice discussion. So, okay, so there is a question already for Eliska. So the question is, programs are now used to optimize aircraft structural parts, but a bug in those programs could cause a part to be too weak. An airplane could crash. How can we prove correctness for numerical geometric algorithms? So this is from Walter. So Eliska, any comments to Walter's question?
Yeah, thank you. So what we have found is that while there are some kind of general guidelines regarding how to implement numerically stable algorithms, the solutions are often very, very specific to the particular algorithm. So I guess I'm not familiar with like those specific geometric algorithms, so I'm not able to answer specifically. But in our paper, we show there are certain math operations that are very general and used in many different domains that are numerically unstable, and those kind of general patterns can be abstracted to create some sort of a more general template that can be used in other domains as well. So yeah.
Yes, thank you very much, Eliska. So, Walter, if you had like follow-up questions, please feel free to just write more or just ask more questions by unmuting yourself. So it's also possible. So let me move on then to the next questions. And the next question is from Jane for Chia Yang. And do you think there would be any difference in your results comparing AI versus traditional control logic if you ran them on physical model versus in simulations? So how confident are you that your result hold in the physical environments?
So first of all, I would say like the performance of AI will be definitely like be shorter in the physical mode than on the simulation plan, since we have for our case, we train the deep reinforcement lane. There will be a shallow or deep neural network inside. So it's for simulation, it's okay. We have powerful computing resource. But when you deploy it on the physical mode, maybe like a automated driving car or UAV or drone, like there are only limited space and power for the embedded chips from computing. For there would be a like quantization problem. You need to quantize and lower your scale of your AI components to fit on the physical mode. So back to the main points. There will be some difference, but for the general aspect, I would say, like I said, the AI has, I would say, like for the automated cars, since like we have 3 benchmarks around the autonomous driving. For this case, the general aspect, the AI controllers can have competitive or even slightly beyond performance compared with the AI one. Or I would say like, because we find that for the control behavior space, I would say there is a hyperplan, like the state space or action space, the policy space. It's really ambitious and challenging to find the optimal solution or policy that can cover the entire situation, entire scenarios. So, just back to point, we have purchased some drones and vehicles in our lab. We want to like deploy our simulation methodologies inside to the physical entities to further evaluate and prove our findings.
Yeah, so thanks for the answer to your question. David said it's okay for us to jump in, so I'm doing that. Yeah, this is actually something we've been thinking about a lot. You know, when you kind of train in simulation, how much, because we work a lot with drones as well. And, you know, so how much can you trust that the algorithms and the experiments and, you know, everything that you run in simulation will really work in the real world? So that's kind of where my question is going, and we don't have the answer either. So
Yeah.
seeing what you would come up with.
Yeah, just like a add-on, like why we choose Simulink is MATLAB, because most of the models are released by the MathWorks. They have been like tested, evaluated, and approved or verified by the professionals or the expertise in that specific domains. So the dynamics inside each plan can be, I would say, precise, can be precise or trustable for the models released by MathWorks. So the dynamics is fine if the algorithms work or fit these dynamics in the simulation. It can be like go too far away in the real entities.
So sorry, just to give one follow-up, but so like, because it's quite impressive. I noticed your paper is a software engineering in practice. So, and you've got these really kind of, you know, real world kind of models. Did they come with kind of metrics of, you know, so basically you just run those models, but they don't tell you anything about the real world aspect of it. You just trust that they were good models, which is fair enough.
Yeah, so as I said, the dynamics released by the MathWorks, I think comparing with some like third-party sources, they are more trustable or worth to
Okay.
be trusted. And
Yeah.
they also come with some documentations to detailedly describe and explain the system requirements, specifications, or dynamics for this platform. So if we find some tricky outputs or state informations, we can go back to plug the equations or like ODEs from the documentation to verify, is this output realistic or possible to jump out?
Okay, great. Thank you.
Yeah, you're welcome.
Many thanks, Jane, for very nice questions, and Chiang for a nice discussion as well. So if you anyone have more questions, please feel free to post them on the chat, right? And then we can discuss them together. So if there's no further question, I can answer some of the questions. So maybe I ask the questions to Houghton. So Houghton, for your work, you are considering like natural language descriptions, right? About this parameters that you want to tune. I wonder, have you also considered looking into bug reports? For example, maybe people have problems regarding certain parameters, and maybe they report some bugs in the bug reports, let's say in Jira. Do you think those things can also be leveraged in addition to the documentation of a particular parameter?
Okay. Thanks for the question. I think bug report can help help SafeTune to provide more knowledge of the trigger condition of some specific side effects on user intentions. But I think we use document because document is the official source of knowledge that can provide more general information on their interaction interaction between the parameter and user intentions. Maybe some I have seen some bug report that has some description of when he set some parameters value to something and a severe reliability issue happened. And I think this is a good source to provide more additional information to improve the quality of the side effects we predicted. Yes, but I think that we should use the document as the main source of information to infer this effect on the other intentions.
Okay, great. Yes, many thanks, Haoshen, for the answer. So we have a question from Jane now to Caroline. So your approach seems to take human perception as the baseline, but often small disturbances in an image can perturb a computer vision algorithm but not affect a human again. Do you have intuition about the scope of vision-related problems that are covered by these experiments? Are human invisible perturbances also a problem?
I'm trying to understand what exactly do you mean. So you're saying that we take changes that affect humans, that do not affect humans, and usually, sorry. So what happened was that what we do is that we take the range of changes that do not affect humans. This is actually a much bigger range of changes that usually people consider in adversarial examples, which is the small perturbations that affect a people study for ML robustness. Actually, through our experiment, MLs do quite well on the smaller range of these changes, surprisingly, but they do quite terribly on the slightly bigger range that people are able to see things clearly, but they do quite terribly. And then what the reliability gap that we saw in related work is that people usually only consider that super tiny range of changes, but actually it was the slightly bigger range of changes that matters, because people can still see with this little bit amount of rain, but ML would fail. But people are not really testing this because they're not these requirements are not specified. Does that answer your question?
I think so. It's kind of hard sometimes getting a hang of the whole paper in a 5-minute talk. So yeah, so I guess, so you looked at kind of perturbances that humans could see and ones that they couldn't see as well then?
Yeah, they are.
Okay.
So we cut the threshold at the change that starts affecting human performance.
Okay, cool. Okay, thank you. Then that should have been a clarification. I'm sorry I missed that, and I should have read the paper first. It's hard with the 5-minute thing now. So thank you.
Right, I'm sorry about that.
Many thanks, Jane, for very nice questions, and Caroline for answering the question. And if you have more questions, please feel free to put them on the chat. So let me add a few more questions in between then. So let me ask a question again, maybe to still with Houghton, just to follow up on just now the discussion. Like, have you also considered like looking into like Stack Overflow as well, or like crowdsource things? Maybe people do talk about configuration that work or does not work. Do you think there is a possibility for it to be incorporated into the analysis of documentation? I understand that your main source of info is the documentation.
Yes, that's very good suggestion. And I think Stack Overflow is very good source to provide more information. Especially we have conducted some experiments on the precision and recall of the prediction, and the result shows that for some types of side effects we predicted, the precision is relatively low. And we think that this is because the training set is relatively small for the software we study, like some reliability. I mean that the configuration parameter may sacrifice security to improve performance, and the security, the parameters that affect the security in some software, the number of them are very small, so they can not provide many training data, and especially the natural language needs some need very huge amount of data. So the Stack Overflow has many in detail these discussions in details, and I think this is a very good way to improve the precision. And actually, we are now extending our paper to a journal version. So I think this is a very good starting point to improve this. Thank you.
Okay, great. Many thanks, Hudson. So while waiting for additional questions from the audience, maybe I ask one question also to Caroline. So Caroline, you mentioned that you measure how good a human is in doing a certain like a computer vision task while perturbations are added to the image. I wonder, would the human's threshold level be different for different images? So let's say you have one image versus another image, they may have a different like threshold. How do you adjust this threshold for different image? Maybe like if the image is at the middle of the night, so it's very dark. So if maybe the human is more sensitive to perturbation, but it's on the broad daylight, maybe they are less sensitive to it. And we cannot possibly do a user study for every single image. So how can you generalize the findings from a set of images to the other group of images that the human didn't see before?
Right, so what we did was that the threshold is evaluated on the distribution of images. So we actually had a research question that I did mention in the presentation that we checked that, for example, if we take the distribution of ImageNet, all the ImageNet images look similar. They're all of the same quality. They're all like similar size, etc. And then actually the threshold will not change if you sample a different set of images from the same distribution. So basically, we had this metric that is generic for different images as long as their initial quality is the same, they're from the same distribution, then we showed that the threshold is actually the same for the same transformation. But different transformations can affect differently, actually.
I see. Okay, many thanks for the answer, Caroline. So we have now a question from Paul. So hi, Caroline. Thanks for the nice presentation. Do you think the choice of IQA metric matters here? Because I see that T_C and T_P vary from 0.48 to 0.94, table 1, across different transformations. Does it mean if someone proposes a new corruption or transformation, they have to calibrate such threshold involving human participants to generate valid test cases for benchmarking robustness? So what do you think, Caroline?
So actually, the thresholds for different transformations are different is because it affects human differently. For example, if I remember correctly, that the one that has the lowest threshold was the color one. So, for example, if we have a picture of a plane on the grassland, which is green, and once you change it into red, it affects how human understands what object is in there. So basically here the value differs because of the transformation. It's not because of the IQA metric, but you are right, the choice of IQA metric does matter here. So usually how IQA metrics are evaluated is by comparing with, they have this data set of human opinions, they compare with the human opinions. So in the paper, we took the one that was state of the art, and obviously, as you suggested, once people build a better one, these will be adjusted, but we have all the data that's posted online, and the only thing that they really need to do is to rerun the IQA threshold again. They don't have to redo the experiment again.
Thank you very much, Caroline and Paul. So Paul, if you have follow-up questions to that, you can jump in, unmute yourself and ask more questions, or just type more of the questions on the chat. Both are okay. Okay, thank you, Paul, for the confirmation. And any further question, feel free to just post it on the chat. So yes. Okay, no questions so far, additional questions. So let me just ask a question to both Eliska and Chayang, because both of you proposed like a benchmark or a data set, right? So how do you think people can make use of this benchmark of data set for their future research? How you envision people using it? So maybe we ask Eliska first, and then Chayang, maybe you can also comment on your benchmark.
Yeah, sure. So we collect our findings into a database, and that database has several columns. It identifies what type of example commit we found in PyTorch or TensorFlow, whether it was a fix or a test, and then it identifies what was the IEEE exception. So that would be overflow, underflow, loss of precision. And then it identifies what algorithm it occurred in. It gives background on the actual algorithm. And then also it shows like what patch was used. So we create some categories of patches. One of them is, for instance, use a different algorithm. So for example, when we calculate simple variance, if we implement variance just per its definition, it's numerically unstable, and instead we should use Welford's algorithm. So that's a good example of use a different algorithm, or reorder the operations in the formula to make it more numerically stable. And it gives these patches and also identifies what type of deep learning topic this issue occurred in. Were we doing data processing, or were we doing neural network quantization, etc.? And then we show the actual like extracted solutions and compare it with the prior solution, kind of like code level solution. And also provide tests. So like each issue is documented as such, and then you can search this database for the topic. For example, you are doing statistical distributions, suppose the binomial distribution, you can search the database and kind of educate yourself what are the issues that could possibly occur, or maybe the results you're getting from your algorithm are not as precise as you would expect. So again, you can search the database for this topic and find what is the problem and what is the solution. And we've used this database to submit a pull request to TensorFlow. There was an algorithm that utilized binary search, and we have found that if we calculate the midpoint index in binary search as per its definition, it can be numerically unstable. And we show there is a different solution that is mathematically equivalent but more numerically stable. So we have linked deep stability along with, here is the issue and here is the solution, and that's why we propose this solution in the pull request. So this is kind of the use that we imagine. And in addition to deep learning developers, we hope that any other software engineers working on numerical or scientific computing libraries can also leverage this, because it can be kind of boiled down to some math formulas that can be used as a template to assess the numerical stability.
Yes, many thanks, Aliska. And just a little bit follow up on that. Are you also imagining your data set to be something like Defects4j, where people can do like testing and debugging work on, and even program repair work on top of your data set?
Yeah, that is one of the uses that we hope can happen. Basically, we hope that some vulnerability detection tool builders can leverage it for the different patterns, and basically then do natural language processing on the code base in question to identify the patterns that could be an issue. So yes, we definitely hope that will be one of the future uses.
Yes, yeah, many thanks, Aliska. So Jiayang, you want to comment on how people can use your benchmark, either from the practitioner's point of view or from a researcher's point of view?
So I would like answer this question from two aspects. So one is the system itself. Like if we get hands-on the reinforcement learning area, we all know there are well-known existing like systems or environments provided by the OpenAI gym, like the double pendulum or mountain cars. So, but if you want to develop some new algorithms or methodologies to handle some industrial level system or heavy load tasks, these like double pendulum or the rocket launch or the mountain cars cannot reflect that complexities. So for the systems we collect from like diverse areas, they can all reflect the complexity of the industrial level applications. And we also summarize and conclude the metrics, specifications, or the requirements about each of the system. If you want to train it, you can just consider our work and make some follow-ups to make the training or the design more easier. And for the another hand, like if you want to leverage some existing AI controllers or agents we have trained for like verification or testing, just like the falsification process, you don't need to train some like new controllers from the ground, because like not everyone expert have like expertise knowledge on the training process. You don't need to like waste time on build some reliable agents, because like even the requirements or the system specifications, you need to fine tune and define the real functions. Neural network configurations or structures or the training hyperparameters to get the like agent with acceptable performance. So if you can, our benchmarks for each of the system, we have built like at least 5, 6, even 9 AI controllers with competitive performance. They have some, maybe some of them have slightly lower capabilities, but they all have some significant advantages or distinct characteristics on some scenarios. So if you want to do some testing or verification jobs, you can just use our existing system and the AI controllers to try it. Yeah.
Yes, okay. That's great. Many thanks, Xiaoyang, for the answer there. Right, so it seems that 2 exciting benchmark being released, and hopefully many more people will benefit from it and use it and make advancement in these 2 directions on numerical stability and also on deep reinforcement learning, right, for cyber physical system. So we still have about 5 minutes. So if anyone has a question, please feel free to just type it on the chat or unmute yourself and share the questions to everybody. Let me just ask one more question. Maybe I go back to Hao Chen. So Hao Chen, I wonder, like, so far your analysis is on the library side. So you look at the documentation of a particular library. Like, for example, I think you analyze a number of projects which are libraries. Have you also considered maybe from analysis from the user side or from the client side? So like the user of those library, is there such a case? And also, have you considered also using fuzzing techniques in order to like explore more of the search space?
Sorry, but you mean the library? Which library may include?
Like, for example, the software that you use, some of them could be a library that is used by some, but they are called by some other code. And then the caller of that code could be, let's say, on GitHub. So there could be many other software that make use of the software that you analyze. Is it possible to infer what is the best configuration setting based on how people have used the configuration setting? So let's say there is this software and a lot of people have been using it and the code are available on GitHub. Is it possible for you to mine how people use that software before in order to infer the best configuration setting?
Okay. You mean then we can mine some useful information from the GitHub and find provide some guidance on how to set a good configuration. Am I right?
Yeah, is it? I wonder, have you? Is it possible? I'm not sure even if it's possible, and if it is like not possible, maybe like I'd like to know more. Like, what is the reason why it is difficult, or is it a possibility to go there?
Let me think. I think mining some knowledge from GitHub can prevent some misconfigurations. And I see some. I've seen some works that mine some the misconfigurations. For example, the people should set one parameter should be set no longer than no bigger than some value, and they prevent some performance issue by suggesting some value range, and help other to set better performance. But I think maybe it will be better to to sum them up and provide more general suggestions from these issues. But I have never thought about this question, and I think that should be very practical. Actually, the reason we conduct this work is we think that helping people tuning performance need too many performance testing for this auto tuner, so it may limit the efficiency and sometimes when the time budget is limited, it's not practical. So I think this is a good way to help people to tune performance.
Okay, many thanks, Hao-Chen. Right, so many thanks to